Hello, gentle readers, fellow earthlings. Reading Foundations today, Easter 2026. It is following on in a discussion as it's ongoing about the recent consideration. The context is as for Hilbert's Nullstellensatz, called the theorem of zeros, yet also in a reading of the etymology of empty star, this sort of account. The Nullstellensatz, a thought experiment or setting, the Ansatz of this. And then for Fritz London, the account of the London condensates with regards to something like the Bose-Einstein condensates for condensed matter physics, about the extremes of the regimes, is about the absolutes here, absolute zero, and temperature, superconductivity, and these kinds of things. There's a reading that Fritz London's account for Albert Einstein's account of the condensate in the infinitesimal, in the absolutes and extremes of the regimes, vis-a-vis usual accounts of atomism and the like, have that, just as from reading Einstein's out of my later years, there's provided, or Einstein's result that he gives, that's what he was working on for his total field theory, was the account of mass energy equivalency in the radially and centrally symmetric instead of the linear. So the unlinear, and that it's founded on its own account, the expression given for this mass energy equivalency among these relations of E equivalency energy and the F Lorentzians, or the invariant theory, that the account of London then has rotons. This is the idea of kind of like, well, waves are spirals and spirals are waves, just is. Got to begin somewhere. Here, that's also considered with regards to waves and wavelets, or these sorts of accounts, or points and intervals, or any other kind of way to look at these sorts of things. That these are particulars that specifically have the confluence and the concordance of what goes into making them for so as a logical and mathematical account for mathematical physics. Then has that the roton of London is also related to Kelvin's and DesCartes' ideas of the vortices for subtle matter, because there's tended to be a thorough account of mechanics here. And so the mechanics then involved there is for the laws of physics and this kind of thing. So then the cube wall concept is given as relating that on one side or the other of gravitational singularity's finite radius's boundary, one side is planar or flat, the other side is spherical or cube, and that the inverse square happens to fit right in the middle between the inverse of this plane and the inverse cube. And so it gives a reasoning why the inverse square, which is usually given as, one of these universal laws of gravitation or the Newtonian account of gravity, has a way to make so that it's derived from these principles of these infinitesimals. And then for the quantum and the quanta, that this is the aggregate and the bulk. This is the model of the theory and all these kinds of things. So reading from London's account is as for Hilbert's account, and I'd bring in Poincare and Dirichlet as the superclassical descriptions of algebraic geometry. Then it gets set up, because the Nullstellensatz is really all about connecting algebra and geometry. That here our algebraic geometry is a geometer's account of geometry for algebra's sake. Vis-a-vis algebra's account of algebra for algebra's sake. Then the voiding the Nullstellensatz, as it were, relates to Hodge duals, the convolutive and involutive settings, and these sorts of accounts and notions of the singular, that singularities in a singularity theory are just branches in a multiplicity theory. And then for the great centrality of invariant theory, as it was in the time of Hilbert and Lorentz, is given for that the Hodge dual and these accounts of algebraic geometry sit outside of that and make a fuller account of that. That is merely a partial or half account, usually received because the entire linear narrative is only so capable of making that so, while being invincibly ignorant in the inductive inference to believe it so. To believe these things then is for the account that all these many connections of the canon and the candidates for foundations in our dogma and doctrine it's intended to satisfy them, to make a satisfying and fulfilling account of the thorough reason here. So that's great, and it's indisputable in a sense, and it's sort of unique account, and we already have one. So then getting back into the specifics of the formalisms for invariant theory, or Hilbert's great account, and then what that means for the quasi-invariant is for this re-Vitali-ization of measure theory, the quasi-invariant measure theory. And then for the continuity laws instead of conservation laws, building conservation laws from a more fundamental continuity law, and these kinds of things. That is the foundations, it has one. So that's a good thing. Books here then, as reading from that, it's about getting into problems of atomic dynamics, or Max Born's book here. This is the London, Fritz London and the Superfluids. This is a little book, Handbook of Knots. So this is more of a practical book. And it's about knot tying and these sorts of things. Raoul Gromont's 428 knots with 47 plates from Cornell Maritime Press, Incorporated. And so I found this among the stacks in the boxes and the shelves and in the library this book is can be very useful to help understand the anatomy of bends and clasps and the tying of knots and untying of knots. For example, about bowlines and bowlines or whatever, with regards to a bunch of different sorts of shanks and hitches and such. The square or reef knot, the most familiar knot to everybody. The square or reef knot is the oldest and most useful method of joining two pieces of cordage. It is used for a large variety of purposes. However, it should never be used if the ropes are of different sizes or materials, as it jams hard under tension. Do not join two hawsers together by this method. The reef knot is formed by tying an overhand knot first, then another overhand knot is formed in the opposite manner and on top of the first one, as the picture illustrates. The running noose or slippery hitch, a Flemish eye knot. So the Flemish knot is you take two braids and you actually unbraid them a bit, and then you pull the braid back around a little bit, and then it forms the Flemish knot is kind of also involved with braids besides knots. And so this is used in things like rigging and cable and the like, because it provides then when you're making an eyelet, an eye of a loop of a piece of cable, then it's much more integral. It has more integrity, the Flemish eye knot here. And then here it's just described as by forming a double figure of 8 in the end of an eye. But that's what it intends to do, is like not just like connecting two pieces of cordage, but also unbraiding them a bit, and then rebraiding their ends together and their pieces to make the Flemish, as it's called. The Hackmore Theodore or Indian bridle. So the bridles, a forbidden bridle of leads of pack animals, usually enough, or horses. It has lots of that involved. So the maritime setting, the stevedore setting and such. The two-strand Carrick diamond knot. Simple knots and mats. So mats are as for making nets and mats, and then ornamental knots. The Japanese crown or success knot. These kinds of things. So this is a great book. It's got a lot about knots in it. The railway senate, the edge plank sling, scaffold hitch, the hoisting hitch. The trucker's hitch is generally considered about one of the best knots to know, is the trucker's hitch, because it allows you to draw into it and then pull it tight in the knot while holding it not tight, whereas other knots like the square knot require there being tension is provided as being static under the load. So the trucker's hitch is a key deal. The running bowline, the jug sling, the hackamore halter tie, miscellaneous hitches and knots. The cat's paw, the skitter's hitch. Many, many knots. The Flemish eye splice, which is a little different from the common eye splice, can be used when there's a tendency for the eye to spread apart. First, unlay the rope of sufficient length for turning in a common eye splice. Select one of the 3 strands and unlay it until the remaining 2 strands are long enough to form an eye of the desired size. Bend these 2 strands down until they meet the single strand A again. Instead of laying strand A up on the standing part, lay it in the other direction, beginning a short distance from the end of the opening strands. B. When strand A has been laid up again, proceed to dispose of the ends as in the common splice. In this illustration, the strands were tucked by using the sailmaker's method, which brings the strands through the rope and along the lay in a uniform manner. So that's just an account of all these things to do with making connections of things and having them hold on their own account. And so it could be related to matters of inference and all these kinds of things that then also is given a nice dictionary of all these terms to do with the language of knots. So much like the language of the theory of graph theory and abstraction, which has all things to do with like directed and undirected graphs, or whether a graph is just a set of edges and nodes, or as about whether the graphs are planar or that to represent them on a plane or in a diagram, they'd have crossings to make for points of intermediacy vis-a-vis other representations of graphs like adjacency matrices and these sorts of accounts, and then the glossary, the vocabulary of the dictionary of the language of descriptive terms of graphs. Then this here has one, for example, that's made about knots, and so this was the practical and then collected instead of abstract and then to be applied. I need to use this for various things. Then we were looking at this Weil's levels of infinity, and so that's where kind of the Nullstellensatz was brought in, is out from here. Weil's selected writings on mathematics and philosophy, edited with an introduction by Peter Pesek, describes a bit of biography of Hilbert. His monumental report on the theory der algebraischen Zahlkörper, theory of algebraic number fields, which he submitted to the Deutsche Mathematiker Vereinigung, is dated as of the year 1897. As far as I know, Hilbert did not publish another paper in this field after 1899. The methodical unity of mathematics was for him a matter of belief and experience. It appeared to him essential that, in the face of the manifold interrelations for the sake of the fertility of research, the productive mathematician should make himself at home in all fields. To quote his own words, "The question is forced upon us whether mathematics is once to face what other sciences have long ago experienced, namely to fall apart into subdivisions whose representatives are hardly able to understand each other and whose connexions, for this reason, will become ever looser. I neither believe nor wish this to happen. The science of mathematics, as I see it, is an indivisible whole, an organism whose ability to survive rests on the connexion between its parts." End quote. Then he talks about physics and being related, and that it's a mathematical physics always, and also statistics is always mathematical as well. A truly great example of far-reaching significance is his mastery of Dirichlet's principle, which, originally springing from mathematical physics, provided Riemann with the foundation of his theory of algebraic functions and abelian integrals, but which subsequently has fallen into a victim of Weierstrass's pitiless criticism. There's a footnote. And then he says Hilbert brought that back in a sense. So talking about the calculus variations, Courant and Morse and these sorts of types, analysts. Full of longing and with uneasiness, they look back upon Euler's era of happy-go-lucky analysis. With Hilbert, rigor figures no longer as enemy, but as promoter of simplicity. Yet the secret of Hilbert's creative force is not plumbed by any of these remarks. A further element of it, I feel, or Weil feels, was his sensitivity in registering hints which revealed to him general relations while solving special problems. This is most magnificently exemplified by the way in which, during his theory of numbers period, he was led to the enunciation of his general theorems on class fields and the general law of reciprocity. So reciprocity and for like quadratic reciprocity is great. It's a great account. It makes for duals and it makes for inverses. And then trying to figure out how that makes for closures is that it makes bridges. And then what are fuller closures, there's still like an inner and outer account of that besides as a product of reciprocity. So the geometric, again, usually enough vis-a-vis the algebraic. Because the algebra can be simple, meaning looking at it as a type of a thing and then treating it as of a type of the thing and then saying these things, so hold to carry for group theory, generally enough, or as for magmas, semigroups and the like. The partials of those, as they're called, and then also with regards to the various attachments of geometric qualities to algebraic qualities and these kinds of things, vice versa and back and forth, has that the algebraization, geometrization, and arithmetization have each their own accounts. And then somehow it's all one account. Is there a group of all groups? Yes, and the operation is composition. On the theory of commutative groups, and when they're number fields, essential progress when Artin later replaced the roots of unity by the elements of the Galois group as values of the residue symbol. Here's what I thought to mention about these accounts of the completions of the rational and algebraic is for rationals and radicals. So radicals are usually the account of roots of things. And furthermore, there's the algebraic extension of those beyond rational numbers. And so these accounts of like the Nullstellensatz and analytic continuation and also complex analyticity vis-a-vis real analyticity and everything what that means with regards to the independence of various conjectures in number theory or Hilbert's problems widely, has that the radicals and rationals then end up being all about roots, so powers and roots. Then here there's accounts of like the roots of unity and how it's to be so that it's like, well, the roots of unity are all unity. And so when things can kind of attain to that, the circle, they're usually on the plane, and the diagram associated with complex analysis, then the radicals are furthermore not rationals. They're irrational. Yet it's different to say then that they're transcendental. And so what gets involved with the fundamental theorem of algebra and the existence of roots and the multiplicity of roots for expressions of polynomials after monomials, that being the fundamental theorem of algebra, then there's whether those there's other aspects of the magmas which are a little bit more general than algebras with regards to how they describe members of under a relation having properties and thus living in a space that eventually relates either to the integer lattice in multiple or any dimensions or the real numbers in any space of them. It has that the radicals make for the rationals for these accounts of completions, then both the bridges that can exist, making for that the powers are iterated and what to make for that the expressions of the guarantees of the existence of roots hold or they don't. And so when talking about voiding the Nullstellensatz is an account of where the rationals and the radicals make for each side of this bridge, they're radical and rational with regards to each other. Either way, one's radical and one's rational. Then as with regards to whether they're commensurable at all is its own sort of account. So yeah, that's what I thought to mention with regards to the invariant theory, and then the quasi-invariant is for making what's then the symmetry-flex instead of symmetry breaking. Because the idea of physics is symmetry breaking is any way that the invariant just doesn't hold and the theory can't stand up, and it would falsify the theory about that. So this is a way to get a little bit closer than just rational and irrational with rationals and radicals. Because at least some radicals are rationals, and at least some rationals, and all rationals, are radicals. So these are the kinds of things. Then that also gets involved with matters of surds and forms, whether surds are harmonies or whether surds are forms. The theory of representations, and this is another most usual account of model theory, is saying it's just like we're modeling this as a group or another algebra or magma. The theory of representations of finite groups, the most systematic and substantial part of group theory, developed shortly before the turn of the century by G. Frobenius, taught us that there are only a few irreducible representations of which all others are composed. See, this is so, but that doesn't mean that they fulfill being each other's roots. So this theory was greatly simplified after 1900 and later carried over first to continuous groups that have the topological property of compactness. It's about Stone-Cech or Stone-Cech and these kinds of things. First to continuous groups, but then also to all infinite groups with a restrictive imposition called almost-periodicity on the representations. Now that's great to know about, this idea of the almost-periodicity, because the periodicity would be key to establish that according to the roots of unity, the radicals are rationals and rationals are radicals, all roots together. And so it is also related to the ideas of the almost everywhere and or almost nowhere from the accounts of measure theory after modern mathematics writ large, because that's where the guarantee is a little looser than guaranteed. And so it's fair to look at that as that's the first point it would break, where it flexes instead of breaking. Then the idea is how it does so, and so that otherwise it would just be found possible that the merest tiniest contradiction and destroy the entire thing, which is not really a goal of trying to stand things up, but according to the rigor, is always possible. So this way, there's an account for that's impossible to have a contradictory theory. While it's still like being able to describe how something like this almost periodicity makes for this representation theory. What it speaks to today is things like faulting purity. So there's this guy named Faulting. He just won the Abel or Wolf Prize or something for mathematics. And then vis-a-vis something like Scholz's perfectoids, which do not have this property. They depend on these accounts of the analyticity and often are just wrapping the old as new, again, after algebraic geometry and haven't lost the way. So faulting purity, though, is kind of the idea is like it's got to be real periodicity. It's got to be not just almost everywhere, but actually everywhere, because otherwise there's anywhere that it could be wrong, that it could come back out. So these are the kinds of things. With these generalizations, one trespasses the limits of algebra. And a few more words will have to be said about it under the title analysis. So separating algebra and analysis and arithmetic has that somehow then they do come back together. And so if it can't really be said to violate the limits so much as it's got to be super classical somehow. At the beginning of the century, algebras seemed to be ferocious beasts of unpredictable behavior, but after 50 years of investigation, they, or at least the variety called semi-simple, have become remarkably tame. Indeed, the wild things did not happen in these superstructures, but in the underlying commutative number fields. In the 19th century, geometry seemed to have been reduced to a study of invariants of groups. No. Felix Klein formulated this standpoint explicitly in his Erlangen program. But the full linear group was practically the only group whose invariants were studied. We have now outgrown this limitation and no longer ignore all the other continuous groups one encounters in algebra, analysis, geometry, and physics. Above all, we have come to realize that the theory of invariance has to be subsumed under that of representations. Or that it's just made it count that there are representations either way and there are invariants either way. To not leave that closed as well. Certain infinite discontinuous groups, like the unimodular and the modular groups, which are of special importance in number theory, witness Gauss's class theory of quadratic forms, have been studied with remarkable success and profound results. The macroscopic and microscopic symmetries of crystals are described by discontinuous groups of motions, and has been proved for n dimensions what had long been known for 3 dimensions, that in a certain sense there is but a finite number of possibilities for these crystallographic groups. In the 19th century, Sophus Lie had reduced a continuous group to his germ of infinitesimal elements. These elements form a sort of algebra in which the associative law is replaced by a different type of law. A Lie algebra is a purely algebraic structure, especially if the numbers which act as multipliers are taken from an algebraically defined field rather than from the continuum of real numbers, omega. These Lie groups have provided a new playground for our algebraists. So these are techniques, and they make for ready partials, and they provide then means of fungibility for tractability after an account of sensibility. And as mentioned here, the discontinuous, the unsensibility, or the dissociated in a sense about these things. So while in this account about this being still the most modern theory today, like all of quantum physics' accounts of group theory are this representation theory after the invariant theory. This is totally standard in all sorts of accounts today. Then trying to avoid the fallacy of writing the old as new has that these other things that are part of aspects of the dialectic simply have to be read again, because otherwise it's just confirmation of bias. And the world doesn't need another account of wrapping that as new again, because it's old. The constructions of the mathematical mind are at the same time free and necessary. So this makes for good reading for this sort of account. Use of infinitesimal qualities like the differentials d epsilon, d eta is horrifying to the modern mathematician, but it is easy to replace them by differential quotients, to which nobody objects. This is kind of syntactic sugar in a sense, but it does not relieve the responsibility of the conscientious mathematician and logician to maintain a rigor. And then he just sets up a co-moving, co-induction kind of a thing. And then that's just weak enough that there's always anti-induction and these sorts of things. Yet it is at least a solve to the concern, if not a panacea. The special form of the Pythagorean law is bound to the special Cartesian coordinates. This Einsteinian conception of gravitation met with complete success, and thus, it's inarguable in a sense. The account of gravity is Newtonian in the limit, and here it's given that this cue ball makes for an account of why that's derived, and it's not just a good idea; it's derived. It's a theorem. But then this idea of the Einsteinian gravitation, or with regards to the geodesy and all this kind of stuff, it's just a formalism. And thus we have to give up the fixed Euclidean metric of the four-dimensional world and replace it by a variable Riemannian metric. Well, it's not necessarily so, because, for example, Einstein has at least 2 accounts of the spatial and spatial, because light and matter are doing different things in the geodesy. And then also there's that the Euclidean becomes Euclidean again, that saying that it's like, well, it's got to be a Riemannian tensor to arrive at basically for the Ricci tensor, the shortest, straightest line between a flat space with no gravity and a deep well of gravity everywhere else. That space-time is reticulated in this way. That it's a simplification to say that is so. This is the point to which I, Weil, had to lead you before I could begin to discuss our central question. The stage on which this frightful spectacle of the world is performed, its extensive space-time medium, is a four-dimensional manifold endowed with a variable Riemannian metric of index 1, but the notion of Riemannian manifold is not bound to the special dimensionality of 4 as far as its metrical structure goes. Any other dimension would do just as well. Why then 4? Here it's an account as after Newton's account of gravity. That's the only account of the three space directions in a ray of time. 4. In discussing this question, we cannot limit ourselves to the metrical structure of spacetime. We have to look at all the laws of the physical phenomena that take place on the stage and ask, can they also be carried in the same cogent and unambiguous manner from 4 to any other number of dimensions, or do they contain something specific for n equals 4? So here there's been discussions about what is the specialness of 3 space dimensions, and then that there's a ray of time is just like, and it's moving. So why it's more a matter of a question of why there are 3 space dimensions, and then that time in the account of the Lorentzian is left on the side. It's after the Laplacian. It's like the opposite plus minus according to the same convention on the Laplacian relating to the metric, which is a rod differential squared at second. That being the Einsteinian formalism that's then intended to connect to this matters of geometry and these sorts of account. That Weil's question is yeah, you can go on forever just adding dimensions to that, but as was mentioned here kind of previously, is like that doesn't really help because nature does it in less, and so what's really relevant is how nature and we believe mathematics does it on its own account, and then why it doesn't need more than 3 and doesn't go more than 3 has many ways to reason why that is so. And then about accounts of like, well, how does the inverse squared arrive as like this universal law for Newton and also for Coulomb for charge, because that's kind of given as like at any given point in time, that's what gravity or the attraction or repulsion of electrical charge says. Has that here again the cube law gives an account the kind of the zeroth laws of physics, why this makes it so. Then he talks about Maxwell's laws, the electromagnetic field in an empty universe, which is a space, which is an ether, and then there's 2 Maxwell's laws. There's E cross B or D cross H. They're rational and radical to each other. Which one comes first? Maxwell says he's like, I'm James Clerk Maxwell. I say either E cross B or D cross H is the relation. One can be defined to then derive the other in terms of it. Which one's primary? I don't say, because then that's already a reductionism of all these other accounts of all the other lettered fields of electromagnetism, magnetism that have that the potential fields are the real fields. So to make a potentialistic account, this is a linear, classical account that Weil is working with here. And then he gets into characters of dimensional indexes, the rank of these, describing the world's causal structure. Locally, that is to say, in the infinitesimal neighborhood of a world point P, the equation of the light cone, ds squared, that being the expression for the metric, and the same as from the Lorentzian, is the sum, or in this tensor notation of the ij's of the g sub ij, according to the tensor summation notation, the convention, of the dxi, the dxj's, those cross equals 0. And that's just saying that there's a constancy, and so that's basically the continuum expression, and it's also set up to be the conservation law and these kinds of things. So this is causality, and that being just that it's the balance of things, and so that's again it for the setting of the Nullstellensatz or Hilbert's. Here, Weil is setting up. This is after otherwise the formalism, and these are the last pieces of the variables left in the thing, and then all pairwise with regards to each of the possible combinations of dimensions. So that said, 0 could also be just the sum of infinitely many terms that are positive and negative with respect to each other. Like the idea of the magic squares and the Latin squares from models of flow and flux. Any way you slice it, it looks like uniform continuous flow, including 0. Yet, any way you pick it apart, it could be not uniform. So that expresses the waves, the currents, the ripples, the eddies, and all these sorts of accounts of flow. Similarly here for the conservation law, why it's a continuity law, that's the more fundamental account. So this is appreciated Weil's account here of all this other stuff that's going on, and that though it's kind of trying to like grow, it has to look to grow to fill out the combinatorial explosion. Otherwise, if all these different things come together, instead of trying to figure out the holographic setting where it comes back and comes down. So a holistic sort of account. And here's some more of Fritz London. And he says, talking about, for many superconductors, the threshold curve can be represented very well by a parabola, yet not exactly. And so it's similarly in all sorts of electrical circuits where it's like, well, what's the behavior of this equivalent series resistance? Or how does it work up that there's something along the lines of the capacitance is defined and by the time constant of exponential decay? It's like, well, exponential is kind of broad because it either starts flat and then drops to at some point in time it's -1 and exponential, and then it's sigmoidal and then goes flat again where there's feedback, or it actually goes around in a circle. So that's kind of the difference relating to exponential is like, well, what do you mean something's exponential? It's like, oh, it grows indefinitely, it grows beyond all bounds. Another kind of exponential is like, what do you mean exponential? Is like, well, sometimes it goes from like 0 to 1 on the way up. That's, I mean, it has to at some point in time, following the exponential curve, change from 0 to 1. And so then the other ideas, what ideas include, for example, it's like, well, why don't we just use a hyperbolic for that? Because that's got a ramp, a smooth ramp. It's like, yeah, but by the time it gets to an inflection point equals 1, that's all the way infinity out. As if you look at the hyperbola or 1 over x, according to the identity line expressing in the first quadrant, the way it's symmetrical around that. Coming from infinity and then reaching a point where it actually has an increment and then going up. So the idea here of the periodic, the cyclical, the exponential, and the sigmoidal are all sorts of various accounts then of just like making a turn at all. So the linear and turns and this kinds of things. So then being able to model something very well by a parabola, which is like the parabola makes for so that both that the integer points on the quadratic or y equals x squared cross the y-axis at the composite numbers and miss all the prime numbers. The quadratic sieve, that's its own world. But then also that every single ray that falls into the well of a parabola bounces and according to incidence or reflection and all go to the focal point parabola. And then there's also the parabola is like, well, the inverse of parabola is the inverse square, because the parabola is just the square as an analytic expression, as a function. And so then it also here is being is very well by a parabola is just as well by an inverse parabola. And so then saying is like, well, if it's not exactly a parabola, then it's kind of like cubed on one side and 1 on the other side. And then whether that's the cube wall concept. And then for what here is called the stop derivative, it's the idea that, so you got any, you know the power law from calculus. You can, for any positive power of an expression, you can raise and lower it according to taking the differential, the derivative, or the antiderivative. You can lower and raise it. And so it goes like, if you take the antiderivative, it goes up in the integral, and if you take the derivative, it goes down to 0. Once it goes 3, 2, 1, 0. So in the negative terms, it's like, well, yeah, I can do the exact same thing for all these numbers except for -1 and 0. Because it's like, is 0 not included in that? It's like, well, 0 is included on the positive side, but on the negative side, 0 is not included. Also, -1 is not included. But all the other numbers are so. Because if you take the integral of x to the -1, it's not something x to the 0. It's ln x, or x ln x, or x to the ln x plus 1. Please forgive me. I would have to look and make some more further derivations about why that is so. But it's trivial, it's commonplace, it's matter of fact. So the stop derivative is saying, is like, well, now we have the stop derivative walk integral, and then this kind of this pause integral and this run derivative. For matters of motion, it's like, well, how is it so that then all that stuff from both sides of the series, it crosses and it goes from negative to positive, or here, positive to negative. Because there's basically a spike at the origin again, and now that's a whole nother non-standard super classical account to be made of these things. So where London's got is like, well, we're going to call it a parabola. And then with regards to the other accounts of like, well, how does it get there for like London condensates vis-a-vis Bose-Einstein condensates? There is a mathematics there, just waiting to be found, and I believe that that's part of it, or the original analysis for the identity dimension and the analytical setting of the stop derivative is it's mathematics in its own way. So these are the kinds of things. He talks about the entropy and the differences in entropy between the normal and superconducting states. This is the running constants of the extremes and regimes, and so on and so forth. So yeah, this also I'm going to be looking to read some more thoroughly. So reading something like Wiles' account, because Wiles' account is descriptive, and so for somebody who knows a lot of mathematics, it's more of a textual account, whereas London's development here is more of a formulaic account, and yet as well that then it points to the odd angles that are involved, and doesn't just end up with a plainly reductionist account, and it is a superclassical account. Max Born, The Problems of Atomic Dynamics. So this box of books still has a bunch of books left in it, and so I'm just going to look at this for a moment. And what I'm looking at is a system of equations, and it's got 3 different terms as related by an index. And then how it's been set up is that the first 2 terms are in terms of some trigonometric identities, the values of the trigonometric functions, expressions in the trigonometric functions. And the third one is of account of also like that, but only 2 of those. So the first 2 are on account of like 3 of those: alpha sine omega t, cos phi sine theta, and then similarly, so it's in 3 different coordinates of the omega, phi, and theta. And then the third one finally is just, well, it's just it doesn't have a third term, so it's missing a term in phi, and where phi and theta are the polar coordinates of the direction of m in a fixed system of coordinates. The motion in the xy plane can be decomposed into 2 rotations in opposite directions. And then it just gives the primes off the x and y side with some coefficients, and breaking out after angle theorems and identities of trigonometry, and offsets, and about the coordinates. And then to these correspond the jumps, where the component q sub z corresponds to jumps m to m. The intensities are proportional to ... and then giving a formulaic account of some derivatives in terms of these identities and the trigonometric functions. If a weak outer field is now established in the z direction, the whole atom rotates slowly around this direction. The circular frequencies of the 2 circular component oscillations are thereby changed slightly as well by their intensities, but in the limiting case of an infinitely weak field, these changes can be neglected. Otherwise, they cannot. And then we have, and he gives an account for this, and says like kind of like the directrix or the director cosines, that this is an account as after the same sort of analysis as director cosine. If these are introduced in the above relations, the formula is given above is shown to be the limiting value of the rigorous formula for obtained through the new quantum theory. So 4 was a root, a radical in terms of some terms. So this is basically taking account of something that's an infinitesimal and then treating it as square or round. And the thing is about mathematical infinitesimals is like, well, they're kind of square and round. And then also there's the idea that in the matters of physics, in the particle and the quantum, it's like, well, mass, length, time, and charge, they in the dimension of these things, they make their own spirals in a sense. These rotons, as I could relate in terms of a formalism that Fritz London wrote, or otherwise these sorts of accounts like Einstein wrote for this centrally and radially symmetric for relativistic account, according to Einsteinian theory. That here Born has another one. Goudsmit, G-O-U-D-S-M-I-T, and Kronig, K-R-O-N-I-G, have used the so-called boundary principle. That is a requirement that the intensities must vanish when either of the states disappears. And so that otherwise there won't be any interacting terms, those kinds of things. The first incentive to the investigation of these intensity laws was the experimental researches on the relative brightness of the components of the Zeeman effect. See, Zeeman basically, he took Faraday's magnetizing the light and said it was nothing. And then set of experiment is like, look, I put blinders on the side. You can't see them. There's nothing. And so what they're talking about here is like, well, yeah, but then they got this brightness to figure out. These, under the direction of Ornstein, who's been mentioned here before, were carried out by Mahlbergers, Dorgello, and others. These investigators at Utrecht first found empirical whole number laws for the intensities in the Zeeman effect and gave simple rules for their calculation. The theory then developed as outlined above. So this gets into low energy and other accounts of when things can be neglected or discarded. So it's not entirely different from Fritz London's accounts of like, well, what happens when they can't be discarded is super that. It's inverse of either way of each other, and so that said, the reductionist account as this would be, and the anti-reduction of this account as they would be, are as well disconnected to be reconnected again. Not discontinuous, just disconnected. And then he talks about corresponding to the classical Larmor procession. The numbers G have been determined empirically by Lande. So this is different by Landau, L-A-N-D-A-U. This is L-A-N-D-E, accent Makut, L-A-N-D-E, as functions of the quantum numbers characterizing the corresponding spectral lines. All attempts to derive these G formulas from classical models led to similar formulas, but never the correct ones. And this is after Planck's. They already added Planck's, so you'd have to deconstruct Planck to get better ones. Here, this account of this is of this. So the usual idea of particles in physics is that they bounce. They're classical, perfectly inelastic collisions. That's the law of the classical law. So the account instead is like, well, if particles are actually so small that they are infinitesimal, then they never really actually bounce. They just orbit and then swing around in the orbit with each other. And so this makes the same account for both collision and reflection, and also just travel. That it's just like a model of bodies that are too small to ever actually collide. Yet they do have their moments and then spin around and fly about. So this is a way to rethink the model of particles. It's like, well, if they're not going to be classical particles, then don't be giving them all their classical properties. Because the idea then for making something like that is like, well, that does make for both accounts of wave mechanics and then particles as interacting, while taking away the account is that the whole idea then is that the classical account of equal, opposite, or rest, mass, and then equal opposite, perfect inelastic collisions. That's after, otherwise, this great account of all these things spinning around at the same time. Interference of surfaces and intermolecular and surface forces. So that's just something that's just opposite, it's antipodal in the great surrounds of what all these accounts otherwise have as a given. But it would really be true then in something like Bohm's account of the pilot wave is automatic and free. So then also all the other derivations, the classical ones, are easily given because there's no way to tell the difference between it, just regular reflection as by collisions in classical mechanics, and this superquantum collision-free orbits the mechanics. See, this next book here is from a scientist, a philosopher in science. His name's Karl Popper, Popper. Karl R. Popper, Conjectures and Refutations, The Growth of Scientific Knowledge. Popper is famous, and here he's talking about forms and ideals. And so Popper's famous in the theory of science because it says, oh, well, we got observation, reproduction, and of experiment for a scientific experiment, and falsification. It's like, well, there's a way to set it up that if the theory wouldn't hold, then it would break, and so you could detect if the theory was just saying nothing. And so, as here's kind of from talking about the radicals and rationals, is like, well, you can find lots of things that are called science today that violate each other. And it's similar when the accounts of the crisis in physics today. It's like, well, do general relativity and quantum mechanics agree? So like, oh yeah, they agree. They agree to disagree about 120 orders of decimal magnitude. And so, and this is a common subject of concern in the entire community of physicists who aren't just coattailing, wallpapering, fudge coding, wall clock watchers of a sort. That it is real, then that the account, then here it goes all the way back to idealism and the analytical tradition, because it's got to be a wider, fuller dialectic from the get-go, and then the principle of inverse instead of non-contradiction. So it's not just contradiction in contradiction itself. And then the principle of thorough reason instead of the principle of just sufficient reason, because it's got to make accounting not just for itself, but itself in all the rest of the world. But these are kinds of things. But anyway, Popper is here talking about Plato and Platonism and these kinds of things. He says, nature of philosophical problems. He's talking about Pythagorean, so the rational. And the Pythagorean is basically it's like, it is rational what this mathematics is and what you'll make of it. It was Plato who realized this fact, in whom the laws stress is important in the strongest possible terms, denouncing his compatriots for the failure to gauge its implications. I believe that his whole philosophy, and especially his theory of forms or ideas, was influenced by it. This is that rationals existed, and having undermined the faith of the Pythagorean order and destroyed the hope of deriving cosmology or even geometry from the arithmetic of natural numbers. I don't agree with that, because you can find numbers from numbers however they go. They're eventually going to have relations that fulfill all the rest of the numbers and mathematical objects. The universe of mathematical objects is complete in a sense. And so Plato has at least so that there's some that are perfect and exist, regardless of whether or not we say so or can find them readily as kind of on the surface of things. That it goes though to show that when Popper is talking about Plato and his ideals, then also he's already kind of shoehorned it into the Socratic and the Pythagorean. Plato was very close to the Pythagorean as well as to the Eleatic school. So the Eleatic school is like Zeno and them, or the classical expositions of the superclassical. And although he appears to have felt antipathetic to Democritus, he was himself a kind of atomist. Atomist teaching remained as one of the school traditions of the academy. This is not surprising in view of the close relation between Pythagorean and atomistic ideas. They're Archimedean, plainly, fundamentally. To have real atomism is the usual idea is that there's infinitesimals, this standard infinitesimals. Here are the iota values, or line rails, they're called. The Xenocrates' account. Because otherwise, this is just Eudoxian and Archimedean, both of them. But all this was threatened by the discovery of the irrationals. So you could think of the irrationals as sorts of radicals that live as like, well, what if the natural numbers run out and so finite natural numbers don't have room to make this anymore? It's like, well, how about they're just not rationals? Okay. Well, how about instead that there are infinite natural numbers and so they just have to be infinite? It's like, well, that's kind of non-Archimedean, isn't it? It's like, well, Archimedes is kind of non-Archimedean if you get right into it. Yet, and that not meant to be facetious, but it is kind of so that the account it makes for it's like there's going to be infinitely many. At least one of them is infinitely grand. So then here's this idea for whether or not it can be reconciled. Atomism, that there are atoms, the uncuttable, and otherwise the infinitely divisible. Is either way, yes, it can be variously. But all this was threatened by the discovery of the irrationals. I suppose that's one way to put it. But was threatened wasn't their being. What was threatened was their conclusion. I suggest that Plato's main contribution to science sprang from his realization of the problem of the irrational and from the modification of Pythagoreanism and atomism, which he undertook in order to rescue science from a catastrophic situation. He realized that the purely arithmetical theory of nature was defeated. I'll disagree with that. And that a new mathematical method for the description and explanation of the world was needed. Thus he encouraged the development of an autonomous geometrical method, found its fulfillment in the elements of the Platonist Euclid. So Euclid was a panel of a man. Here we have an account for axiomist geometry that gives Euclid's elements. And furthermore, it has not just that the parallel postulate is independent, but also the double angle axiom of sorts is independent. Euclid's otherwise axioms. And so here as well, this is a nice reading, though, of the intuitionistic account of what to make from the Pythagorean catastrophe, or the existence of radicals in otherwise rationals. That still said it doesn't exactly make it so. Then why Euclid's elements repaired that? Euclid instead say it's like, well, as long as we're talking about numbers, here's geometry, which has its own account in mathematics. You can say that mathematics is geometry. You can say that mathematics is number theory. Then having it be both of those is its own sort of account. That is part of mathematics. Why it's all got to be one theory, descriptive theory. And for representations after descriptions, that's the theory of there being mathematics, all the theory of all the mathematical objects. So here Popper talking about Plato as putting up Euclid as somehow putting away the number theoretic concerns of the Pythagoreans for the geometric concerns of the Euclideans. It doesn't really say that much, except that it's that's not so much the old wrapped as new as the shifting the goalposts, I guess you might say. So Popper writes, what are the facts? I shall try briefly to put them all together. Pythagoreanism and atomism in Democritus' form were both fundamental based on arithmetic, that is to say, on counting. So atomism in Democritus' form is basically saying is like, hey, you know how these are infinitely divisible? I postulate also that there are indivisibles. So to say that there's countings for things like the sand reckoner and stuff like that is not the same. He's saying these are uncuttable and they're uncountable too, because otherwise they wouldn't be. So yeah, Democritus is more of a counting of dual monism and just saying is like, hey, we're going to have atoms exist. Anyways. Now, that could be two co-inductive accounts that Popper has here, but nobody else needs those. You can have a deductive account. 2, Plato emphasized the catastrophic character of the discovery of the irrationals. Yeah, so what? You can look at Zeno's arguments as being entirely paradoxes or necessarily not paradoxes. Here they're necessarily not paradoxes, because otherwise nothing would ever smoothly happen at all. That coming up in about to the hour then. Yeah, what I want to talk about today was radical rationals, and then the ideas of the completions of things, and as for the cube wall, and that the cube wall is an account of how otherwise these formalisms of physics make for theorists like Born and Hilbert and these sorts that make the 20th century what it is, that this is the 21st century. And we have not just the 20th century, we have all the ones from before that too. So that's the account today then. Radical rationals revisited. Warm regards then, gentle readers. Good day. Happy Easter.